Wagwan, my GCSE science students. In today's video, we're going to be looking at chapter 9, which is crude oil and fuels, which covers chemistry paper 2 if you're doing the AQA science board. Now, in this video, we're going to be looking at hydrocarbons, fractional distillation of oil. We're going to be looking at burning hydrocarbon fuels. And also, finally, in this chapter, we're going to be looking at cracking hydrocarbons, okay? All right, let's get into this. Okay, so let's go. Now, first thing that you need to know for this chapter is that crude oil is a mixture. It is a mixture of hydrocarbon, okay? So crude oil is a mixture of hydrocarbon. And here I have a nice beaker of hydrocarbon. Now, in that mixture, you have your hydrocarbons, and each hydrocarbon has a different length, a different chain length, okay? So if you look at this hydrocarbon here, which is ethane, and we get to the naming later, it has 2 carbon in its chain length. But if you look at this one here, right, which is that mixture of hydrocarbon, it has 5 carbon and so forth. So crude oil, this here, it's a mixture of different hydrocarbon. Now, what is a hydrocarbon? A hydrocarbon, it is a compound, which means that it is chemically bonded, all right, and it is made up of hydrogen and carbon, and I would say that it is made up of hydrogen and carbon only. So your simplest hydrocarbon would look like this, methane, okay? Good, and that's a hydrocarbon. Why? Because it has carbon and hydrogen only, and it's a compound because it's bonded. And right here now we have a covalent bond, okay? Good. Now, where did all of this crude oil come from? Now, crude oil, it takes millions of years to form, okay? Good. And it is currently running out, all right, because we're using it faster than it can be replenished, and we say that it is a finite resource, or it's a non-renewable resource. Now, it comes from these tiny sea creatures and planktons, and what happens is when they die, they then fall to the bottom of the seabed, okay? And when they fall to the bottom of the seabed, what then happens is that over time they then become covered with layers of mud and sand and all of that. It covers it up. Now, because they are now covered up, over time, this causes heat and pressure, and because of the lack of oxygen, because they've been covered by the layer of sand and dirt and everything, over time, it's then converted into crude oil. Now, it's important that you know these steps, okay? Good. Now, moving on. Now, crude oil, it is not useful in its current form, okay? These hydrocarbons, they're too big and they all have different boiling points, so it is not useful. Now, how can we get it to become useful? We need to separate all of these hydrocarbons, all of these big hydrocarbons which have different sizes, okay? We need to separate them into their fractions. And a fraction is what we call a group of hydrocarbon, and they have similar boiling points, they have similar weights, they have similar properties. Now, how are we going to do that? This is done using a process called fractional distillation, okay? So the reason that this is done, for example, this hydrocarbon here, it would have a specific boiling point, okay? But if you compare it to this hydrocarbon here, which is bigger, it's going to have a higher boiling point. So the boiling point of the hydrocarbon is dependent on the size of the hydrocarbon. The bigger the hydrocarbon, the bigger its boiling point, because you're increasing the intermolecular forces. So we're going to have to use fractional distillation to separate the crude oil. Now, you must know the process of fractional distillation. Now, in step 1, here I have my mixture of hydrocarbons, okay? Notice that some are big, some are large, okay? So I have my crude oil of different sizes. So the first thing that you need to note is that in your fractionating column, it is on a temperature gradient, okay? So it is hot at the bottom and it is cooler at the top, okay? So what happens then? Your crude oil is heated. So you're changing the oil into a gas. It's heated to roughly about 350 degrees Celsius. It's heated to very high temperature. Now your oil is now going to be changed into a gas. Okay, so it now enters as a gas, and as it enters as a gas, the really big hydrocarbons, those have a very high boiling point. So what's going to happen? They're going to condense. Okay, so what's going to happen straight away? The large molecules, they're going to condense as a liquid straight away, okay, the really big ones. But your small hydrocarbons, they're going to travel further up the column. Now, as those smaller ones travel further up the column, when they reach their specific boiling point, they're going to condense depending on their sizes, okay? And the smallest one will get to the top, and each fraction is now condenses at its boiling point. So now what you have is separation, okay? So you need to know exactly how that process works. So your really big hydrocarbons condense at the bottom. The smaller ones, or the smallest ones, those go to the top, and each fraction, depending on their sizes, which will then affect their boiling point, they will condense at different sections of the fractionating column. Okay, good. Now each fraction which comes out at the different points on your fractionating column, they all have different uses. So for example, the residue which comes off at the bottom, which is referred to as bitumen, okay, that's used for that's used for making roads, lubricating oil. Then above that you have your diesel oil, which is used for diesel engines such as your trucks, your lorries, your buses. And then above that you now have your kerosene oil, which is used as your fuel for jet fuel. Above that you then have naphtha, which is used to make different chemicals. Then you have your petrol, okay, which is, as you know, is used in cars, and then you have a refinery gas, which is used as fuel. Okay, so what you need to know, the ones at the bottom, those have the biggest chain length. Okay, so the ones at the bottom, those have the biggest chain length. The ones at the bottom always are very viscous, which means that they're quite thick. Okay, but the ones at the top, they're the most flammable. Okay, so these here would be most flammable. Okay, and these would be least flammable. Okay, these would be least flammable. Okay, so what you realize is the ones at the top, those are really, really good fuels. Okay, so these here are good fuels. So the smaller the hydrocarbon, the better the fuel, the less runny it is, and the shorter it is. Okay, good. So next thing now that we need to note is most of the hydrocarbons inside the crude oil, most of those are what we call alkanes. Now, you possibly don't quite remember what an alkane is. Now, alkanes, we describe them as being saturated. Saturated meaning that they have single bonds only, okay? So saturated means they have single bonds only, okay? And because carbon is in group 4, so carbon is in group 4 of the periodic table, it can have a total of 4 bonds, okay? Because carbon, when you look at your periodic table, it looks something like that, which means that its electronic configuration is 2, 4, so it can have a total of 4 bonds, okay? And there is carbon, which is bonded to 4 hydrogen. And this is all single bonds, and because when they have all single bonds, it is full, there's no other atom that it can be bonded with, we refer to this as being saturated. Okay, good. And this is called methane. Now you need to know how to name these hydrocarbons, okay? And the name of the hydrocarbon is dependent on the number of carbon inside the hydrocarbon. So this one, the first one here, is methane, okay? So the prefix that we use here is meth, 1 carbon. Good. Then your next one is ethane. So when it is 2, we use the prefix eth, okay? So the prefix eth means 2, All right, and you can see the formula there, CH4. Then you go to C2H6. So the next one is going to be propane. Good. Prop. Good, which means that it's 3 carbons. Good. And then the next in line is going to be butane, C4H10. Okay, and it can go on and on until 1,000, 2,000, any amount of carbons that you'd like. Okay, so the prefix here is going to be but. All right, which is 4. Okay, so if you think about your next in line, are you able to think what your next in line is? Look at the trend. So your next in line is going to be C5H12. Okay, and if you're going to draw that one out, you're going to have 5 carbons bonded to the hydrogen there. So the 3, this carbon can hold a total of 2. That carbon can hold a total of 2. This carbon can hold a total of 2. That one can hold a total of 3, okay, as it has 1 bond there. And this one, we would call that one pentane. Okay, that one would be called pentane. All right, now you have different mnemonics that you could use to remember them. And this one is my elbow points backwards. Okay, methane, ethane, propane, butane. Okay, good. Now here is a general table that you could use to fill this up. So butane, that's going to be C4H10, and then this is going to be C5H12. So you should realize that there is a trend, and by displayed formula, what we mean is you're doing the drawing. Okay, so you could then take this table down. All right, I'll do the first 2. You could use the previous part of the video to then complete your table. Okay, so you should realize that there's a trend as you go down, and that trend is what we refer to as the general formula. Okay, so the general formula, it is CnH2n plus 2. So whatever the number of carbon that you have, you're going to have twice the number of carbon plus 2. So for example, we did pentane before, which is C5. 2 times 5 is 10. Add 2, which is going to give you 12. Okay, and if you draw that out, you'd realize that we did it earlier. You'd realize that how you get the 12 hydrogen. Okay, drawing that really quickly. Okay, good. So N stands for any number. You can have any number of carbon there. So for example, if I had 60 carbons, it's going to be 2 times 60, which is 120. Add 2, 122. Okay, good. And you need to know that. So this is the general formula for alkanes. Now there is another type of hydrocarbon which is also sometimes found in crude oil, all right, and those are called alkenes. Now straight away you should see the difference between an alkane and an alkene. Alkene, they are unsaturated, which means that it contains at least a double bond. So if you can see the diagram here, there is at least a double bond. Okay, so I have the first 2 here. I have ethene, propene. Thinking about the table that we did before, we're now going to try and draw butene. Okay, how would you draw butene? The prefix but means that there are 4 carbons. Okay, good. You're free to put the double bond anywhere. I'm going to put the double bond in the middle. Okay, remember we said that a carbon is allowed 4 hydrogens. So sorry, well, 4 bonds rather. 1, 2, 3, 4. So that carbon is full. This carbon has 1, 2, 3. So I'm only allowed to put 1 hydrogen, which now makes it 4 bonds. So 1, 2, 3, 4. Then this one, 1, 2, 3. You're only allowed 1 more. Then 1, 2, 3, 4. Okay, good. So my formula here is going to be C4 H 1, 2, 3, 4, 5, 6, 7, 8. So it's going to be H8, okay? Good. And then this one would be C2, H4, and then C3, H6. So you should see that there is a trend there. And what is that trend? That general formula, okay, that general formula is going to be CnH2n. I will have twice the number of hydrogen as I do carbons, okay? So we've done butene on the next page, okay? Good. That's not what we want there. We want the formula, okay? So we need the formula there. So it's going to be C4H8. That's going to be C5H10, because remember, it is following CnH2n. And remember, you must have your double bond, okay? You must have your double bond. So C3, there at least have to be one double bond. So 1, 2, 3, 4, 1, 2, 3. This carbon is only allowed one. This carbon has one bond, therefore it's allowed 3 more. Each carbon is allowed 4 bonds, okay? Good. And I will let you try the last one for yourself, okay? So you can try drawing pentene for yourself, okay? So it is CnH2n. So that's alkenes versus alkane, okay? Now we're going to look at combustion. Now what is combustion? Now combustion is a reaction in which a fuel reacts with the oxygen in the air as it burns. And this is what we refer to as an oxidation reaction, because you're reacting a fuel in air. Now you can see here I have two different flames, and what do you notice with the difference here? This one, it is a yellow flame, okay? This one, it is a blue flame. Now you'd have seen this at school by opening and closing the air hole. So if you have a look here, the air hole is closed. Air hole closed, which means that there is not enough oxygen, okay? And we refer to that as being incomplete combustion. So there are two types of combustion. You have incomplete combustion, and you also have complete combustion, in which in this bit here, the air hole is open, okay? So there are two types of combustion, complete and incomplete. So for complete combustion, no matter the hydrocarbon that you have, once you combust it, meaning that you're reacting it with oxygen, you will always produce carbon dioxide and water. And then for incomplete combustion, you're going to produce 3 different products, okay? You're going to have your hydrocarbon, so that shouldn't say hydrogen, okay? That is a mistake. You're going to have your hydrocarbon that's going to react with oxygen, and it's going to produce carbon, carbon monoxide, and water, okay? Good. So notice the difference here. So also, let's look at the difference between the two. So for complete combustion, you have excess oxygen, okay? You have a lot of oxygen. For incomplete combustion, you have a limited supply of oxygen, okay? What are my products here? My products is carbon dioxide and water. Those are my 2 products. But for incomplete combustion, you're going to produce something called carbon, which is referred to as soot. You're going to also produce carbon monoxide, and you're also going to produce water, as there's not enough oxygen to completely oxidize, okay? So this is referred to as soot. Soot is that black substance which is produced when you're burning. All right. Now, in terms of flame, the color of the flame, this one is going to be a blue flame, and this one is going to be a yellow smoky flame. This is because of the production of the soot, okay? A yellow smoky flame. All right. Now, the other thing that you need to be able to do, you need to be able to write balance equation for combustion. So, for example, methane here, all right, methane, one carbon, reacting with oxygen to produce water and CO2. Okay, the best way to balance these equations is to go in this order: C, H, O. Okay, so on this side I have one, on this side I have one carbon, on the left side I have 4 hydrogen, on the right side I have 2 hydrogen, and on the left side I have 2 oxygen, and on the right side I have 3 oxygen, 2 and another one there, 3. Okay, good. So my carbons are fine, but if I look at my, let's use a different color. If I look at my hydrogen, it is not fine. So what are we going to do? We're going to times that by 2, which makes it 4. You take that 2, you put that 2 in front of the compound in which it is found. So we're going to put a 2 there. That 2 also affects my oxygen. So my oxygen now is not 3, it's now going to be 2 and another 2 there, which makes it 4, which means I need to times this by 2. That gives you 4. You're going to take that 2 there, put in front. Equation is balanced. 1 carbon, 4 hydrogen, 2 times 2, which makes it 4 hydrogen, 4 oxygen, 2, 2, 4. Equation is now balanced, okay? We will try another tricky one in this case. Now, in this case, we're reacting ethane, we're combusting it, which means that we are reacting it with water, okay? And it forms carbon dioxide. It also forms water. The best thing to do, CHO, CHO. Good. This one is a slightly tricky one, but not difficult. So we have 2 there. We have 1 on that side. We have 6 hydrogen on the left. We have 2 on that side. We have 2 there. We have 3 oxygen. 2 and another one makes it 3. Okay, so let's use a different color. How am I going to get the same on the left as the right? We're now going to times that by 2, which gives me 2. I take that 2, I put that 2 in front. Okay, and my next in line is 6, so I'm going to times that by 3, which now makes it 6. Where do I put that 3? In front here. So now I have 2 times 2, which is 4. Add 3, which makes it 7. So now I have a total of 7. How can I get 7 on this side? That's going to be pretty difficult. But to get 7, we can times it by 3.5. Okay, that gives me 7. So I'm going to put that 3.5 there. However, as you know, we are not allowed like decimals at GCSE level. So what we will do is we will have to times the entire equation by 2 to remove that 3.5, okay? Bearing in mind there's also 1 there. So my new equation is going to look like this. I'm going to have 2 C2H6 plus 2 times 3.5, that's now going to give me 7 O2, which then gives me 2 times 2, which now gives me 4 CO2 plus 6 H2O. Let's check if it's balanced. 2 times 2 is 4. I have 4 there. C2H6. 2 times 6 is 12. Now I'm going to have 6 times 2 is 12. Okay. 7 times 2 is 14. 4 times 2 is 8. Add 6, which gives you 14. That's the most difficult one that you will get to balance. And they would tell you that it is excess oxygen, which therefore lets you know that is complete combustion. Okay? Now, the final bit for this chapter is, if you look at this graph, what it is showing is that for your very small hydrocarbons, the demand is great than the amount you get from the crude oil, okay? So your small hydrocarbons, they're in demand. Reason being, they're extremely good fuels. These are really good fuels because, as we mentioned earlier, the smaller the hydrocarbon, the better it burns, okay? Now, you also realize that the big hydrocarbons, your fuel oil, your diesel oil, all right, you have lots of it, okay? You're getting more than it is in demand. Now, is there a way that we can convert the big hydrocarbons into smaller hydrocarbons since they're more in demand? Of course there is. And that process is what we refer to as cracking, okay? We call that cracking. Now, why is cracking important? As we mentioned earlier, the lighter fractions are more in demand because they're more useful fuels. All right. However, more than half of those molecules in a typical batch of crude oil contain the bigger one. So the bigger one, we have lots of that. Okay, so we use a process of cracking, which converts our large hydrocarbons into small hydrocarbons. Okay, good. Now, this is the general equation for cracking. You have a large chain alkane, all right, and under the right conditions, a high temperature and a catalyst, you will break it down to form smaller chain alkanes and also an alkene. So remember, the alkene, there is a double bond, and the alkanes, it is single bond only. Okay. Good. So this is what they use in school to carry out the cracking. This is the cracking apparatus. Okay. Good. So you can see your paraffin there, which is a really huge hydrocarbon. It is heated. It goes over your broken pot, which is used as a catalyst. Okay, and then it travels down here, and then it is collected as your gaseous product. Okay, good. So for example, we have decane. And when you break decane, which is 10 carbons, you will get an alkane and you will also have alkene. So if you notice here, 5 plus 3 is 8, add 2 is 10. It must add up back to give you whatever you started with, okay? So you have 12 plus 6, that's 18. Add 4, that gives you 22. It must add up to give you back there. So, okay, so now let's have a look at doing some cracking equation, okay? So you have 10 carbons here, so we started off with 10 carbons and you've produced 6 carbon on this side, which means my missing amount of carbon, okay, so to work out carbon is going to be 10 minus 6, which gives me 4. That's going to be C4, okay, and my hydrogen is going to be 22 minus 14, which gives me 8. So that's going to be C4H8, okay? So this right here, that is going to be my butene, okay? Because I have twice the amount of hydrogen there, and this is now going to be hexane, okay? And also on to the next one, okay? Let's have a look at this. So we started off with C2H4. Straight away that I know that is ethene. Okay, so my other product has to be an alkane. So that has to be C10 because 10 add 2 gives me 12. Okay, and it's going to be H22. How do I know that? It's going to be 26 subtract 4, which gives me that bit there. So my missing bit there, it is dodecane. All right, don't worry about the naming of these compounds. All right, so here's another one. So what's my missing product? So I have 4 and 2, 6. So my missing product has to be 6 because it needs to add up to give you 12. And I have 8, add 4, which is 12. Okay, so that's going to be H. So, yep, so it's going to be 26, take away 12, and that's going to give me 14, okay? That's going to be my missing hydrogen there. Of course, they could ask you to do the drawings for these as well. Finally, you need to know how to test for alkenes. Okay, so to test for alkenes, you use something called bromine water, and this is what bromine water looks like here. It's like a red brown liquid, all right, or orange. Okay, good. Now if an alkene is present, what will happen? It will change to being colorless. So alkene plus bromine water, it will change it to be colorless. But if it is not an alkene, it will stay orange. Okay, so if you have an alkane with bromine water, there will be no reaction. So just to summarize that, if you have an alkane, there's no change to the bromine water. But if you have an alkene, it will decolorize bromine water. Okay, and that is it for this video. All right, thank you for watching. Make sure that you subscribe and share my content with your friend. And remember, I am out.